We're now going to talk about what happens when we extend the particle in a box to multiple dimensions. In other words, what happens when we actually have a three-dimensional box that we can put the particle in. So my model is now that the potential, a function of x, y, and z, is equal to 0 between the values of x equals 0 and a, y between 0 and b, and z between 0 and c. Anywhere outside of the box, the potential is infinity. Here's a diagram. I've drawn out my box, my x direction, my y direction, 0 to b, and my z direction from 0 to c. I set up my Schrodinger equation. What do I have? Minus h bar squared over 2m. Now I have this monstrosity. Second partial derivative with respect to x, plus the second partial derivative with respect to y, plus the second partial derivative with respect to z, operating on psi equal to e psi. The best way to solve this, and really the only way to solve this, back up a second. The problem with this is that I have multiple dimensions. And the way to reduce this from one differential equation with three variables is to separate it into three differential equations with one variable. The way I do that is to set up a product wave function. We're going to do this with the hydrogen atom as well. Instead, we'll have functions in r, theta, and phi. Here, for the particle in a box, psi of x, y, and z is equal to a product of three functions. Capital X is a function. So this function x, which is a function of x, variable. Okay. Function y, a function of the y variable. Function capital Z, which is a function of the z variable. And now what I'm going to do is I'm going to distribute this. I'm going to apply this onto this. And when I do that, and I'm going to drop the explicit dependence on x, y, and z, and these x, y, and capital Z. And what am I going to get? For my first term, y and z are not functions of x. Therefore, this will be equal to y, z, second derivative of the x function, second derivative of the x function with respect to x squared, plus the same thing here. Second derivative of y will go through x, act on y, doesn't care about z. So x, z, second derivative of y with respect to y, and of course last one plus function x, function y, second derivative of the function z with respect to z squared. I end up with this. And this is then equal to, and if this is equal to times the constant of minus h bar over 2, which I've neglected, then it turns out I can separate these into three separate equations. I can factor out x, y, and z, and what I'll get is three equations. The first one, minus h bar squared over 2m, second derivative of the x function equal to e in x, x function, 2m, second derivative of the y function with respect to y equal to the energies with respect to y, and then minus h bar squared over 2m, second derivative of the z function with respect to z squared equal to e z function. This looks complicated, but you know what? We've already solved these. This is the particle in a box. This is the particle in a box. This is the particle in a box. And so what I have is that my x function then is just equal to square root of 2 over a sine nx pi x over a. Y is a function of y is equal to the square root of 2 over b sine ny pi y over b, and the z function is equal to the square root of 2 over c sine nz pi z over c. There are my solutions for the three-dimensional particle in a box. Now, I've left with one last piece which I want to get to. I'm going to go back to the other side of the board and erase. I want to talk about the concept of degeneracy. Imagine that A is equal to B is equal to C. Then all the energies are the same. By the way, the energies are also the same for each of these as well. So I should have written this in. The Ex is equal to nx squared h squared over 8 ma squared. The energy for y is equal to ny squared h squared over 8 mb squared, and so on. But for now, let's set A is equal to B is equal to C. What do I have for states? I'm going to write a set of my quantum numbers, three quantum numbers, nx, ny, nz. And so my lowest energy state is going to be 1, 1, 1. What's my next energy state going to be? I'm going to have one quanta of energy, but I can put it in either x, y, or z. That can be 1, 1, 2, 1, 2, 1, or 2, 1, 1. And so I see three energy levels. Those three energy levels, because of the same energy, we call them degenerate. I think you can see that what happens if A is unequal to B is unequal to C. Now the degeneracy breaks on these. And so these all get a little higher, a little lower. As we get to more and more quanta of energy, the various states that can be occupied get fairly complicated.